Welcome to our deep dive into electrostatic potential and capacitance.
Oh, that's a mouthful.
It is. We're exploring Chapter 2 from your Class XII Physics textbook.
From India's NCERT.
Yeah, exactly. Which
Yeah.
they've generously made available for everyone to see.
Yeah. So anyone around the world.
Yeah, we're focusing on, if you are a 15-year-old student out there.
Yeah. This chapter builds on what you learned in Class 11 about potential energy.
Right, and brings in the electric force. It's really about understanding how charges interact and store energy.
Yeah. Which is fundamental to so much of our technology today.
Absolutely. Now let's start with a quick recap. So back in Class 11, you learned about potential energy. Think of lifting a book.
Mm-hmm.
You do work against gravity.
Right.
And that work is stored as the book's potential energy.
Exactly.
Similarly, if you push a spring, you store energy in it. These are examples of conservative forces at play, where the work done only depends on the starting and ending points, not the path taken. Now bring in Coulomb's law from the last chapter. It tells us about the force between electric charges. This force, like gravity,
It's also conservative.
yeah, is similar to gravity.
But instead of masses, we have charges.
Okay, so just like lifting a book against gravity, if we move a charge against the electric force of another charge, we do work and store potential energy.
Right.
Now here's where electrostatic potential comes in. It tells us the potential energy per unit charge. Imagine bringing a tiny positive test charge from very far away to a point near a bigger charge.
Okay.
The work done per unit charge is the electrostatic potential at that point.
And one important thing to remember is it's the difference in potential that matters, not the absolute value.
Oh, okay.
Just like we measure height differences, not the absolute height from the center of the Earth.
All right.
We often set the potential at infinity to be zero as a reference, but the key is the potential difference between 2 points.
That makes sense. Now let's look at the potential created by a single point charge.
Think of it like a tiny ball radiating an invisible potential field. The further you move away, the weaker this potential becomes. The formula for this is VR equals Q over 4 pi epsilon, not R,
Okay.
where Q is the charge and R is the distance from the charge. Notice this potential decreases as 1 over R,
Okay.
which is slower than the electric field strength, which decreases as 1 over R squared.
So the potential fades away more gradually with distance compared to the electric field. And this formula works for both positive and negative charges, right?
Absolutely. A positive charge creates a positive potential around it, and a negative charge creates a negative potential. This makes sense when you think about work. Bringing a positive charge closer to another positive charge requires work because you're pushing against repulsion.
Okay.
But bringing it closer to a negative charge, you're helped by the attraction, so the work is negative.
This potential idea is pretty neat. Now things get a little more complex with electric dipoles. Can you remind us what those are?
An electric dipole is simply two equal but opposite charges separated by a small distance. They're surprisingly common. Think about water molecules. They are polar, meaning they have a positive and a negative end, just like a tiny dipole.
Right, and dipoles have a dipole moment, P, which tells us about their strength and orientation.
Exactly. Calculating the potential due to a dipole can be a bit tricky, but if we focus on a point far away from the dipole, the formula simplifies to VR equals P dot R hat over 4 pi epsilon, not R squared.
Okay.
Notice this depends on the angle between the dipole moment and the position vector, meaning the direction matters.
So if the dipole is aligned with our position, the potential is stronger.
Yes. And another key difference is that this potential falls off faster with the distance as 1 over R squared,
Okay.
compared to the 1 over R for a point charge. This means a dipole's influence is more localized than a single charge.
So we've seen the potential due to a single charge and a dipole.
Yeah.
What about a whole bunch of charges?
Luckily, we can use the principle of superposition. The total potential at a point is simply the sum of the potentials due to each individual charge.
Okay.
It's like calculating the total light in a room from each bulb.
So no matter how complex the charge distribution, we can always break it down and add up the contributions from each charge. That simplifies things. Now, this next concept sounds a bit mysterious. Equipotential surfaces, what are they?
Imagine a map showing areas of equal altitude. Those are contour lines. Equipotential surfaces are similar, but they represent regions in space where the electric potential is the same. No work is done when you move a charge along an equipotential surface, just like walking along a contour line doesn't change your potential energy due to gravity.
So equipotential surfaces are like electric flatlands.
That's a good way to put it. And here's a crucial point. Equipotential surfaces are always perpendicular to electric field lines.
Oh,
Think about it. If the electric field had a component along an equipotential surface, it would do work on a charge moving there, which contradicts our definition.
that makes sense. The electric field lines must cut through those equipotential surfaces at right angles.
Exactly. Visualizing this can be helpful. For a point charge, the equipotential surfaces are like concentric spheres, and the field lines radiate outwards, always perpendicular. In the uniform field, the equipotential surfaces are parallel planes with the field lines perpendicular to them. For a dipole, the shapes are more complex, but follow the same rule.
So we have these invisible surfaces mapping out regions of equal potential, and the electric field lines tell us the direction of force a charge would experience. It's like a hidden landscape guiding the movement of charges.
That's a great way to think about it. And this relationship between the electric field and potential can be described mathematically, too. The electric field E is the negative gradient of the potential V. Mathematically, that's E equals negative dV over dl, where dl is a tiny displacement perpendicular to an equipotential surface.
So the electric field points in the direction where the potential is decreasing most rapidly, and its strength tells us how steep that decrease is.
Precisely. Just like on a steep hill, the force of gravity is stronger, and in regions where the potential changes rapidly, the electric field is stronger. Now let's shift gears a bit and talk about the potential energy of a system of charges.
Okay, we've talked about potential energy before, but how does it apply to multiple charges?
The potential energy of a system of charges represents the work needed to assemble those charges, bringing them in from infinitely far away to their current positions.
So for two charges, Q1 and Q2, separated by a distance R1, 2, the potential energy would be U equals Q1, Q2 over 4 pi epsilon, not R1, 2.
Exactly. And this equation tells us a lot about the interaction between charges. If the charges have the same sign, the potential energy is positive, meaning you have to do work to bring them closer. But if they have opposite signs, the potential energy is negative, meaning energy is released as they come closer.
That makes intuitive sense. Like charges repel and opposite charges attract.
Precisely. And we can generalize this to any number of charges. For example, for 3 charges, you'd consider the interaction between each pair and add up their contributions to the total potential energy. It's a bit more bookkeeping, but the same fundamental idea applies.
So the total potential energy tells us about the energy stored in the entire configuration of charges. But what if we place this system of charges in an external electric field? How does that affect the potential energy?
That's a great question, and it leads us to another important distinction. We need to consider both the interaction between charges within the system and their interaction with the external field. So for a single charge Q in an external potential VR, its potential energy is U equals QVR.
Okay, so we add the potential energy due to the external field to the potential energy of the charges interacting with each other.
Exactly. And for a system of 2 charges, the total potential energy would include the potential energy of each charge in the external field plus their interaction energy with each other.
So it's all about carefully accounting for all the interactions.
It is. Now, before we dive into the next section, let's pause here for a moment. We've covered a lot of ground already.
Yeah, we have.
We've explored the concept of electrostatic potential, looked at the potential due to point charges and dipoles, and even discussed the potential energy of a system of charges in an external field. We'll pick up next time with an even more intriguing configuration, an electric dipole in an external field. Stay tuned.
Okay, see you then.
Welcome back to our deep dive into electrostatic potential and capacitance. Last time we left off with the idea of potential energy in a system of charges, especially when those charges find themselves in an external electric field.
Yes, we were just starting to explore what happens when we introduce an external field into the mix. It seems like things get even more interesting when we consider a special case, an electric dipole in an external electric field.
You're right. Dipoles in external fields behave in fascinating ways. You see, a dipole in a uniform electric field experiences a torque, a twisting force that tries to align it with the field. Think of a compass needle aligning itself with the Earth's magnetic field. A similar principle is at play here.
So there's a force trying to rotate the dipole.
Exactly. And this rotation is tied to a change in potential energy. The potential energy of a dipole in a uniform electric field is given by U equals negative P dot E, where P is the dipole moment and E is the electric field.
So the dipole's potential energy depends on its orientation relative to the field.
Precisely. When the dipole is aligned with the field, its potential energy is at a minimum. Think of it like a ball rolling down a hill. It naturally wants to reach the lowest point. Similarly, a dipole tends to align itself with the field to minimize its potential energy.
And when the dipole is anti-aligned, its potential energy is at a maximum.
Exactly. It's like the ball being at the top of the hill. It's in a less stable position. This potential energy difference explains why dipoles experience a torque. They are constantly trying to move toward the state of lower potential energy.
Okay, that makes a lot of sense. So we've covered a lot about charges in electric fields, but what about conductors? How do they behave in electrostatic situations?
Conductors with their free-moving charges are quite special. One key property is that the electric field inside a conductor is always zero in electrostatic equilibrium.
Wait, why is that?
Imagine applying an external field to a conductor. Those free charges inside will immediately start moving in response to the field redistributing themselves until they create an internal field that exactly cancels out the external field. This happens incredibly quickly.
So the charges rearrange themselves to shield the interior from the external field.
Precisely. It's like a self-organizing force field within the conductor.
Yeah.
And because the electric field is zero inside, the electric potential is constant throughout the conductor.
So every point inside a conductor has the same potential.
Exactly. Think of it like a water tank. The water level is the same everywhere inside. Similarly, the potential is uniform within the conductor. Now, at the surface of the conductor, things are a bit different. There, the electric field is perpendicular to the surface and has a magnitude of E equals sigma over epsilon naught, where sigma is the surface charge density.
So the electric field jumps from zero inside to a non-zero value just outside the surface.
Yes. And this behavior has a remarkable consequence: electrostatic shielding. Imagine a conductor with a cavity inside. No matter what electric fields are present outside the electric field inside the cavity is always zero.
Wait, so the conductor acts like a shield, protecting the cavity from external electric fields?
Exactly. This principle is used in Faraday cages, which are enclosures made of conductive material that block electromagnetic fields. They are used to protect sensitive electronic equipment and even people in certain situations.
That's amazing. It's like having an invisible force field.
Yeah.
So conductors have these unique properties due to their free charges. But what about materials that don't conduct electricity? Well, like insulators. What are they called in electrostatics and how do they behave?
In electrostatics, we call insulators dielectrics, and they play a crucial role in understanding a device called a capacitor, which we'll get to soon. Unlike conductors, dielectrics don't have free charges that can easily move around. Instead, when you apply an electric field, the molecules in a dielectric become polarized.
Polarized. What does that mean?
It means that the positive and negative charges within each molecule shift slightly, creating tiny electric dipoles. Imagine a bunch of tiny compass needles all trying to align themselves with the applied field.
So each molecule becomes a mini dipole.
Exactly. And these induced dipoles, in turn, create their own electric field that opposes the external field. They don't cancel it completely like in a conductor, but they do weaken it.
So the presence of a dielectric reduces the electric field strength.
Precisely. And the extent to which a dielectric can weaken the field is characterized by its dielectric constant, denoted by K. A higher dielectric constant means a stronger reduction in the electric field.
Okay, that makes sense. So dielectrics modify the electric field within them. But why is this important? Where did this idea of a capacitor come into play?
Capacitors are where dielectrics truly shine. A capacitor is essentially a device that stores electrical energy. It consists of two conductors separated by an insulator, which is often a dielectric material.
So like two metal plates with some insulating material sandwiched between them?
Exactly. When you connect a capacitor to a voltage source, like a battery charges, build up on the plates, positive charges on one plate and negative charges on the other, this separation of charges creates an electric field between the plates and energy is stored within this field.
So the capacitor is like a tiny energy reservoir.
That's a great way to put it. The amount of charge a capacitor can store for a given voltage is called its capacitance, denoted by C. A higher capacitance means it can store more charge for the same voltage. And guess what plays a key role in determining capacitance?
Dielectric material.
You got it. The presence of a dielectric between the plates increases the capacitance. Remember how dielectrics weaken the electric field? This weakening allows more charge to build up on the plates for the same voltage, effectively increasing the capacitor's storage capacity.
That's clever. So by choosing the right dielectric material, we can control the capacitance of a capacitor.
Exactly. Different dielectric materials have different dielectric constants, and this allows us to fine-tune the capacitance for specific applications. Now let's look at a simple yet incredibly useful type of capacitor, the parallel plate capacitor.
Okay, what's special about parallel plate capacitors?
As the name suggests, it consists of two parallel conducting plates separated by a distance d.
Mm.
If we assume a vacuum between the plates, the capacitance is given by C naught equals epsilon naught A over D, where A is the area of each plate and epsilon naught is the permittivity of free space.
So larger plates or a smaller distance between them leads to higher capacitance.
Precisely. Now, if we introduce a dielectric material between the plates, the capacitance increases by a factor of K, the dielectric constant. So the new capacitance becomes C equals Kc naught.
So the dielectric effectively multiplies the capacitance.
It does. And this is one of the key reasons why dielectrics are so important in capacitors. They allow us to create capacitors with much higher capacitance for a given size, which is essential for many electronic applications.
This is fascinating. It's like we can engineer capacitors with specific properties by carefully selecting the dielectric material.
Exactly. Now, you might be wondering, can we combine capacitors to get even more diverse capacitance values?
That's a great question. I'm guessing the answer is yes.
You're absolutely right. Just like we can combine resistors in series and parallel to create different resistance values, we can do the same with capacitors. There are two basic ways to combine capacitors in series and in parallel.
And these different combinations affect the total capacitance of the system.
Precisely. When capacitors are connected in series, the total capacitance is less than the capacitance of any individual capacitor. The formula for the equivalent capacitance of capacitors in series is 1 over C equals 1 over C, 1 plus 1 over C, 2 plus ... where C1, C2 ... are the capacitances of the individual capacitors.
So it's like adding resistors in parallel. The total resistance is less than any individual resistor.
Yeah, that's a good analogy. And when capacitors are connected in parallel, the total capacitance is the sum of the individual capacitances. C equals C, 1 plus C, 2 plus ...
So it's like adding resistors in series.
Yeah.
The total resistance is the sum of the individual resistances.
Exactly. These combinations allow us to create capacitors with a wide range of capacitance values, which is crucial for designing electronic circuits.
This is all coming together so well. We've covered potential dipoles, conductors, dielectrics, and even how to combine capacitors. But there's one more piece of the puzzle. I'm curious about energy. We've talked about capacitors storing energy, but how do we actually calculate that energy?
That's an excellent question, and it's the perfect bridge to the final part of our deep dive. The energy stored in a capacitor is directly related to the charge it holds and the voltage across its plates. We'll unravel these connections and explore the fascinating world of energy storage in capacitors next time. Stay tuned.
Welcome back to the final part of our deep dive into electrostatic potential and capacitance. We've covered a lot of ground from the basics of electric potential to the intricacies of capacitors.
We have.
Now let's tackle that burning question. How do we actually calculate the energy stored in a capacitor?
It all boils down to the work done to charge the capacitor.
Okay.
As we pump charges onto the plates, we're working against the electric force, and that work gets stored as potential energy within the electric field between the plates.
So it's like stretching a rubber band. The more we stretch it, the more energy we store in it.
Exactly. And we can quantify this stored energy using a few different formulas. One common formula is U equals 1/2 QV, where U represents the energy, Q is the charge on the capacitor, and V is the potential difference across its plates.
So the energy stored is proportional to both the charge and the voltage.
Precisely. And we can also express the energy in terms of capacitance. C, using the relationship Q equals CV. Substituting this into the previous formula gives us U equals 1/2 CV squared.
So if we increase the capacitance or the voltage, the energy stored in the capacitor increases.
Exactly. This highlights why capacitors with larger capacitance are better at storing energy, especially when operating at higher voltages. But we can go even deeper and connect this energy to the electric field itself. Remember, the energy is stored within the electric field between the plates.
Right. So how do we quantify the energy stored in the field?
We use the concept of energy density, which tells us how much energy is stored per unit volume of space. Think of it like the concentration of energy within the field. For a parallel plate capacitor, the energy density denoted by U is given by U equals 1/2 epsilon, not E squared, where E is the electric field between the plates.
So the energy density is proportional to the square of the electric field strength.
Precisely. This means that regions of stronger electric fields store more energy per unit volume. It's like a more intense electric field holds more energy.
This is all making so much sense. It's amazing how energy, capacitance, voltage, and electric field are all intertwined in the capacitor.
It truly is a beautiful interplay of concepts. Now, before we wrap up, let's shift gears for a moment and think about what happens when a capacitor discharges. Where does all that stored energy go?
That's a great question. It can't just vanish, right?
Absolutely not. The energy gets transformed into other forms, such as heat or light, as the charges flow through a circuit. Imagine a camera flash. The sudden burst of light is powered by the rapid discharge of a capacitor.
Wow, that's a great example. So capacitors aren't just about storing energy, they're also about releasing it in controlled ways to power various devices.
Exactly. Their ability to store and release energy quickly makes them essential components in a wide range of electronic circuits, from power supplies to audio equipment to timing circuits.
This deep dive has been an incredible journey. We started with the fundamental concept of electrostatic potential and explored how it leads to the idea of capacitance. We learned about the different types of capacitors and how they store energy within their electric fields, and we even touched upon their diverse applications in the real world.
Indeed, it's been a comprehensive exploration. And remember, the world of electrostatics is full of wonder and practical applications. Keep exploring, keep asking questions, and you'll continue to uncover the amazing ways in which electric charges shape our technological world. I will. And to all our listeners out there, we hope this deep dive has sparked your curiosity and given you a new appreciation for the invisible forces that power our everyday lives. Keep those brains buzzing, and we'll catch you in our next deep dive.